Hi everyone, this is Professor Любимцева with GPY 100 Physical and Environmental Geography. And this week we are talking about climate zones, climate classifications, and also climate change. So our learning objectives this week is to define what is climate, to discuss approaches to climate classifications. We would focus particularly on Köppen climate classification and would also discuss natural and human-induced causes of climate change and trends of climate change. So in all the previous chapters, we mainly focused on weather. You all are already familiar with the concepts of climate and weather. And let's just refresh what are the differences. So climate is the average of weather conditions. You can think about it, about what you're wearing today versus your dressing style, where what you're wearing today would be your weather and how you usually dress would be your climate. Or you can think of the mood, right? The way how you feel right now versus your personality. The study of climate is concerned with both average values and their variations through the year. Definition of climate zones are primarily based on temporal and spatial patterns of precipitation and temperature, but also some other aspects of climate. And there is a variety of different climate classifications. Climate classifications are necessary for many purposes. There are empirical classifications, genetic classifications, and applied classifications. In empirical classifications, climates are grouped based on annual averages and seasonal extremes of temperature and precipitation. And Köppen classification that we are going to use and which is described in this chapter is the prime example. There are also genetic classification systems. They rely on information about climatic elements of solar radiation, air masses, pressure systems, and so on. Those are more difficult classifications to create and to use because of the multitude of variables. And these type of classifications are more relevant for climate modeling. And then there is a variety of applied climate classifications that can be used specifically for agricultural crops or specifically for water availability and so on. So our chapter 8 is focusing on Köppen classification systems, and all different climate zones here are broken down into major types such as tropical humid, dry climates, moist mid-latitude climates, severe mid-latitude climates, polar climates, and highlands, and they're all labeled with different letters, as you can see on this map. A for tropical, B for dry, C for temperate, and D for severe, and then P for polar climates. So let's take a look at different types. So tropical humid climate, those are moist climates. They're associated with areas very close to the equator. They extend northward and southward from the equator, somewhere in the range of 15 to 25 degrees latitude. So this is your AF, or tropical wet, is a tropical climate where precipitation occurs all year long. Then AM is tropical monsoonal climate. This is where annual rainfall is equal to or greater than what we see in AF, but most of the precipitation falls usually during the 7 to 9 hottest months. And then tropical wet and dry, or savanna climate, AW, has a much more extended dry season during winter. So those are climates where we have very wet summer and dry winter. This is how climagraphs for those different types of climate look. Here are some examples of AF as Iquitos in Peru, or AW, for example, in Dakar, Senegal. Now, dry climates are labeled with letter B, and there are two major groups. BW, those are dry, arid. Those are your desert climates. Those are true desert areas. They cover about 12% of the Earth's land, and they're dominated by the xerophytes, the xerophytic vegetation that can survive in desert conditions. They can be labeled also with small letter H or small letter K, and this is how we distinguish between the dry, arid climates in subtropics which is letter H, and then in mid-latitude with letter K. And then BS, those are dry semi-arid climates, so the climates of dry grasslands or steppes, and they cover about 14% of the Earth's land surface, and they receive a little bit more precipitation than in BW, either from the intertropical convergence zone in the tropics or from the mid-latitudinal cyclones. So here we see some examples of the pattern of temperature and precipitation, for example, in daily waters in Australia, or in Tindouf in Algeria, or in Las Vegas in Nevada. Next, we have mild mid-latitude climates. They are labeled with letter C. And again, here we have three groups: CFA, humid subtropical, CS, Mediterranean, and CFB, marine west coast. So humid subtropical is a climate with hot, muggy summers and frequent thunderstorms. And then winters are usually mild, and precipitation is falling during the season and is coming from the mid-latitudinal cyclones. On the other hand, the Mediterranean climate receives most of rainfall in winter season from mid-latitudinal cyclones, and then summer is usually dry and hot, and resembling their BS climate all the year around. And then CFB is the climate of, it's a marine climate of western coasts. You would find it along the western coast of the United States. You would also find it along the western coast of Europe. It has humid climate all the year around, sometimes with very short dry summer. So here we have some examples such as CS climate in San Francisco in California, or CFA climate in Memphis, Tennessee, or CFB, the western coast in Vancouver, British Columbia. Next, we have severe mid-latitude climates. They are labeled with letter D. Those are moist continental mid-latitude climates that have warm to cool summer and cold winters. And winters are severe with snowstorms, with strong winds, with bitter cold from continental polar or Arctic air masses. Just as in sea climates, there are three major types, right? There are three varieties of D climates: DW with dry winter, DS with dry summer, and DF, which is wet all year around. Again, we can look at some examples of climographs, right? The climographs are the charts showing you the annual distribution of precipitation and temperature. And so we see here some examples such as Duluth, Minnesota with DF, or Yakutsk in Siberia with DW. And then polar climates are labeled with letter E. Polar climates have year-round cold temperature with the warmest month less than 10 degrees centigrade. There are two minor climate types within this group. This includes ET, which is polar tundra. It's a climate where the soil is permanently frozen to the depth of hundreds of meters, and this condition is known as permafrost. And then EF, and this is the climate of polar ice caps, where the surface is permanently frozen and basically there is no vegetation at all. So again, we can look at some examples such as McMurdo in Antarctica with EF, and then Barrow in Alaska with ET. So you see this example of permafrost. And finally, the climates of highlands. Those are the climates of very high altitudes. They can be found anywhere in the world, in any climate zone where we have very high mountains, and they are labeled with letter H. So now we are going to talk a little bit about climate system, and from there we will go to climate change. It's important to realize that climate is more than just what's going on in the atmosphere. Everything is connected in the climate system. The atmosphere is connected to the ocean, to the terrestrial vegetation, to soils, to hydrographic network on the continents. And of course, there is lots of connectivity between what's going on in the atmosphere and what's going on in the ocean. And more, it's also interconnectedness with human society. The human society is a part of climate system, and we are increasingly altering the system much faster than any other geological force. So let's take a look at different causes of climate change. Let's start with natural causes of climate change. This includes, but not limited to, Milankovitch variations, changes in the solar activity, changes in atmospheric transparency, changes in the ocean circulation, and volcanic eruptions. So Earth geometry theory or Milankovitch cycles tell us that the distance between the Earth and the Sun is changing, and it's changing in the cyclical fashion. So there are indeed three astronomical cycles, 96 or 100,000 year cycle, 40,000 year cycle, and 20 to 21,000 year cycles. As you can see, those cycles are very, very slow, but they do affect our aphelion and perihelion, that the concepts that you are familiar with from our first chapter. So the distance between the Earth and the Sun is gradually changing, and the latitudes of our tropics is also changing. You know from the previous chapters that the tropics are right now at 23.5 degrees in the northern and in the southern hemisphere. But over time, this angle of the tilt of the axis of the Earth has been changing between 20 degrees and 25 degrees. So let's keep this in mind, and as we are looking at the geological records, we can clearly see the pattern of these three cycles overlapping, showing us variability of the temperature in the past. Now, of course, those changes are very, very slow. If we examine, for example, the bubbles of air from the ice cores that are found in the ice of Greenland or in Antarctica, scientists can actually measure what exactly were the concentrations of carbon dioxide and other chemicals in those bubbles of air. And if you plot those concentrations of carbon dioxide and other greenhouse gases together with the global temperature, you would have pretty accurate picture showing correlations between the atmospheric carbon dioxide concentrations and the temperature changes over very long periods of time. Like here we see it over the past 150,000 years, but these data now are available over 800,000 years. So it's a long period of time, much longer than our span of observation. What is troublesome, however, is what we see right now. So the current levels are already significantly higher than compared to what the Earth has experienced in many thousands and hundreds of thousands of years. So there is no doubt that in addition to those natural causes of climate change, we humans are increasingly modifying our climate system at a much faster pace. This chart shows us how we can separate human and natural influences of climate. So what we see here, the black line, the black chart is actually showing the observations from meteorological stations all over the world. So this is a very, very accurate record of global temperature all over the world. And then the purple part of the graph is showing us the combination of natural and human factors. And the green part of the graph is showing us only natural factors. So if indeed only natural factors were changing our climate, it would be much, much colder today, and the temperature would be at least 2 degrees lower. You can clearly see that it's starting with 1960s and 1970s, that there is divergence between the purple line showing us natural and human factors, and the green line that is showing only natural factors. So there are four major groups of factors in the way how humans are affecting climate. The first one is, of course, the emissions of greenhouse gases. There are three other ways how we are changing climate: through the tropospheric aerosols and through pollution of our clouds, through the depletion of stratospheric ozone layer, and directly through land use and land cover changes. Historical data for this century from all meteorological centers from all around the world tell us very similar stories. So what we see here, the data from NASA, from Hadley Center in UK, from NOAA, and from Japanese meteorological agencies, they all tell us how the temperature has been changing over the past few decades. And there is absolutely no controversy today that climate change that we are experiencing now is the product of human activity. There is a very strong correlation and overwhelming evidence that the spike of temperature increase that we have been experiencing during the past century, and especially since the middle of the past century, has been associated with human activity. We are dumping today 110 million tons of man-made global warming pollution into the atmosphere every 24 hours. So there is no surprise that our atmosphere is heating at the unprecedented rate. And why is this happening? The emissions of greenhouse gases, the emissions of carbon are coming from these major sectors, from electricity production, from industry, from transportation, and globally about 25 or 24% is also coming from land use and agriculture, but in developed countries such as the US, that will be actually only about 9 or 10%. So really most of this is energy generation, transportation, and industry. This is where we need to think about climate change solutions. A couple of other areas that I want to point out where human impact is also happening, and it's important to understand that also, although greenhouse gases are contributing into warming, some forms of atmospheric pollution, such as industrial aerosols, can actually slightly contribute into temporary cooling. This cooling is much, much smaller compared to global warming, which is caused by greenhouse gases. But cloud pollution and contamination of the atmosphere with, for example, products of burning of coal can actually create those areas with temporary cooling. Now, why aerosols are harmful? Not just because the impact on climate, but they're primarily also dangerous for human health. They are causing asthma, they're causing lung cancer. So obviously aerosols from burning coal are dangerous for us. The third area where humans are impacting climate is the depletion of O3, the depletion of ozone. So the ozone layer is associated with the low portion of the stratosphere. You all are familiar with stratosphere. It's the next layer after the troposphere, and human activities that release pollutants into the atmosphere, pollutants such as chlorofluorocarbons, actually destroy the ozone layer. This was major problem in the 1980s, like when I was growing up, when I was your age in 1970s or 1980s, that was a huge problem. Today, the concentrations of CFCs have been stabilized, they're much lower, and so the hole in the ozone layer is not growing anymore. In fact, it has been a little bit repaired. It's still an issue, but it's not anymore super alarming issue as it was in the 1980s. And this really gives me hope that if all the countries could come together to solve the problem of the ozone layer, we could very well do the same now and address the problem of global warming, which is caused by our emissions of greenhouse gases. And finally, the last but not the least, I also want to remind that land is both a powerful sink, but also emitter of carbon dioxide emissions. So the way how we use our land does matter. It does have impact on climate change. And so this is the difference between the amount of CO2 which is produced as we use land and the amount of carbon dioxide which is sequestered by land, by vegetation and soils. So there is a net benefit from our land systems. And we need to remember that the way how we practice our agriculture can be actually very beneficial for climate if we do it right, if we don't destroy soils, if we don't till the soils, if we practice agriculture involving many species that can that help us to sequester some carbon. So agriculture is not just the problem causing climate change, it can also be a great solution for climate change. And of course, planting more trees, planting more vegetation, just recreating land cover, which is capturing more carbon. That's the best way to address the problem, and in addition to cutting emissions of CO2. So number one solution is to cut the emissions, to move as quickly as possible from the use of fossil fuels to the use of renewable energy. And today, the cost of solar energy, the cost of wind energy is already lower than the cost of heavily subsidized in this country fossil fuels. So we can accomplish this transition very quickly. The technology is here. The science tells us this is the right thing to do. We just need to have good policies in place, and we definitely can do it. Climate change is a solvable problem. So, and then of course, the second way how we can address this is also by helping to support our land cover and protect vegetation and plant more trees. I'm going to leave you here with one announcement. So if you want to learn this week more about climate change solutions, I hope that you will join GVSU for its annual celebration of the Climate Change Education Solutions Summit. It's going to be this Thursday. And this is also an opportunity for you to earn up to 15 points of extra credit. The summit consists of 3 webinars, and each webinar you can be used as your either virtual community engagement paper or as an extra credit event. And so for each of these webinars, you can write a 5-point paper, 1 to 2 pages. You can submit it through the Dropbox, which is available on the Blackboard by Friday evening. And so if you use another event for virtual community engagement, you can actually use all 3 of them for your extra credits. So registration is closing tonight. It's closing at midnight. So if you haven't registered yet, I strongly recommend to attend. Again, you can attend the entire event or part of the event. You can attend it for extra credit or just for fun. I'm going to leave you here. See you next week.